So I think that this conference has a very appropriate topic. There is a gulf between what theoreticians can prove about algorithms for NP-hard problems and what practitioners observe. And I want to talk a little bit about that gap between theory and practice. Is this the right button? Yes. So let's talk about what we can learn from worst-case analysis of NP-hard problems. Is there anything we can learn that would be encouraging for to the individuals that have to solve those problems? We can't look to exact solution methods for much good news because the running time is almost surely exponential in the worst case. Polynomial time approximation algorithms give bounds on the quality of solutions to NP-hard optimization problems, but in practice those approximation ratios are usually unrealistically high. So again, we see a gap between what is achieved in practice and what theory, based on worst-case performance, tells us. Another approach is parameterized complexity, where we where we associate with the instances of an NP-hard optimization problem certain parameters, and we can sometimes prove that for small values of that parameter or particular values, the running time is polynomial. But typically in those cases, the dependence on the parameter is also very adverse. So again, we don't get much satisfaction from the results of parameterized complexity. An area that I worked on for a long time in the 70s and early 80s was probabilistic analysis, in which the problem instances are drawn from simple probability distributions. And in those cases, one can often prove excellent performance on the average or with high probability. But practitioners tend, in fact, both theoreticians and practitioners tend to look with some disdain upon those results for different reasons. Theoreticians because they believe in worst case, and practitioners because they don't believe that the probability distributions that are postulated in probabilistic analysis correspond very well to the instances that come up in practice. So again, probabilistic analysis is limited in its predictive value for what will happen when you actually run algorithms for NP-hard problems. On the other hand, heuristics, about which we can prove very little, are often unreasonably effective. And it seems to me then that we need systematic methods for choosing among heuristics and searching in the space of heuristics for good solutions. I think the talk that Kevin Leighton Brown gave this morning is a very good step in that direction. So I believe that there's a lot to be done, more in the spirit of statistics or machine learning than in the traditional spirit of worst-case complexity theory, about empirical testing of heuristics on training sets of representative instances. I won't go into that too much in this talk, but I hope in the panel discussion that we can get into this. Here are a few of the well-known examples of unreasonably effective heuristics that perform well for reasons we can't explain. Large traveling salesman problems can be solved with typical percentage errors around 20% by extremely quick and dirty tour construction methods. Local improvement methods do better, and cutting plane methods, which are the most sophisticated ones that we have, also tend to perform well, although giving exact optimal solutions for longer running times. For graph bisection problems, there are local improvement methods that empirically are found to give near optimal solutions. Perhaps the most striking example is the fact that huge satisfiability problems are routinely solved rapidly by branch and bound methods, so that in some fraternities like the model checking fraternity or digital design fraternity, satisfiability problems are often thought of as easy rather than hard. The greedy set cover problem typically gives reasonably good solutions, even though its worst case performance is terrible. And we find in practice that well-tuned integer programming codes like the Cplex code tend to perform well in many instances for reasons that we can't explain. So I think a fundamental problem in the field is to see if there are any general principles that would explain the seemingly unreasonable success of the various heuristics that we have. In this particular talk, I'm just going to present a couple of case studies, if you will, in the development of a heuristic algorithm, starting with, typically with a fairly naive algorithm, and then modifying it to get better performance. So I won't be talking about tuning or validating heuristics in depth, but simply giving a couple of examples of algorithmic development for NP-hard problems. My first example comes from molecular biology. It has to do with protein-protein interactions. So proteins interact to form aggregates, or sometimes they're called modules, sets of proteins that work together that interact to perform some cellular function. So we can think of a living cell as a collection of little molecular machines, each consisting of a bunch of interacting proteins. So the study of the interactions between specific proteins is essential for understanding cellular function. And we can summarize the known information about protein-protein interactions in a particular species by what's called the PPI network, the protein-protein interaction network of the species or the organism, in which the vertices represent proteins and the edges indicate the presence of physical interactions between proteins. It then becomes plausible that a graph theoretical analysis of these, of such a structure could reveal subgraphs that are interesting and likely to represent useful aggregates of proteins. Those subgraphs would tend to be connected and to have small conductance. The particular problem from this domain that I want to talk about is called the querying of protein-protein networks. And it depends on the notion that problems that cells have to solve the solutions to those problems tend to be preserved from one organism to another in the course of evolution, so that you would, if you find an aggregate of proteins that has a certain function in human, there should be a related aggregate in similar species. And key to this notion of relatedness is the idea of orthology between proteins. So two proteins are said to be orthologous if they have evolved from a common ancestral protein. Of course, without knowing the course of evolution, we can't exactly identify them with certainty, but comparing their sequences and structures, we can get an indication of which pairs of proteins from different species are likely to be orthologous. So this suggests the following problem. Given an aggregate or collection of proteins in species A and the protein-protein interaction network of a second species, find a connected subnetwork in the subnetwork of the second network, which has minimum size and contains at least one protein orthologous to each protein in S. So the idea is that you have information in species A that a particular set of proteins work together, and you want to find information within the network for species B of orthologous proteins to those which form a compact connected structure and might be solving the same problem in that second species. So mathematically, we're led to the following graph theoretic problem, which also has other interpretations that I won't go into for social networks and other kinds of structures that are represented by graphs. Given a graph G, a set of colors C, and an assignment of a color to each vertex in the graph, find a connected subgraph with a minimum number of vertices containing at least one vertex of each color. So the idea is that you're looking for in the protein case, you're looking for a connected set of proteins. You want the set to be small, and you want small incardinality, and you want to find within it an ortholog of each of a given set of proteins. So the color of a protein, the color of a vertex in the graph corresponds to the protein in your query that a given vertex is orthologous to. So for the purpose of the talk, I'll discuss a special case of this problem, which we'll call the strong version, in which your connected subgraph is required to have exactly one vertex of each color. So to summarize, the problem is simply this. You have a graph, you have a color on each vertex, and the color may be repeated many times at different vertices of the graph, and you want to find a connected subgraph containing exactly one vertex of each color. This version of the problem is NP-hard, even in the case of trees of maximum degree 3. So what I'm going to do is lead us through a couple of different approaches to solving this problem, starting with relatively naive approaches and then elaborating them to get better algorithms. So one approach to this problem is via dynamic programming. In the dynamic programming approach, you can make a table of the following relation with two arguments, a vertex v and a set of colors s. And let the predicate b of vs be true if the graph contains a tree rooted at vertex v, which contains exactly one vertex with each color in s and no other vertices. And the predicate is false otherwise. So if we could tabulate this predicate for all vertices v and sets of colors s, then by probing this table for the case where s is the set of all colors, we will find out whether there's a connected subgraph containing exactly one vertex of each color. But we can tabulate this predicate for all v and s by a simple recurrence going from smaller cardinalities of the set S to larger cardinalities. And the running time will be proportional to the number of vertices n times 3 to the kth power, where k is the number of colors. So this gives us an algorithm which is quite acceptable when the number of colors is small. The problem can also be tackled by integer programming. So we can formulate an integer program which expresses the following constraints. We're looking for a set of vertices x such that x contains exactly one vertex of each color. And we also have to express, so that can be easily expressed by linear integer inequalities with an indicator variable for each vertex indicating its presence or absence from the set. A little trickier is to express the property that the chosen vertices induce a connected subgraph. And we can use the following trick, which is due to my coworker Falk Höfner. We ask that in the subgraph induced by the set of vertices, which should include one vertex of each color, there exists an integer-valued flow in which one arbitrary vertex is the sink for cardinality of x minus 1 units of flow, and each of the other vertices is the source of 1 unit of flow. So the idea is that if we're looking at a connected subgraph consisting of the vertices in x, there should be a spanning tree, and if we direct all of the edges of the tree toward one particular vertex, then that vertex can be the sink of the indicated set of unit flows, one from each of the other vertices. So we can augment the integer program with additional variables that represent the flows in the different edges. And in that way, we'll come up with a linear integer program with 0, 1 variables to indicate membership in x and integer variables representing the flows in the edges. And by solving that program, we can determine if there's a feasible solution to the colorful connected subgraph problem. So integer programming is of course pretty hard, and we can only empirically measure how this algorithm would perform. And we found that it does perform acceptably in many cases, but now I want to lead us to another algorithm which we have found to perform considerably better. The starting point for this algorithm is the solution of a relaxed problem. In the relaxed problem, we designate a subset of the colors as constrained. Typically, these will be the colors that occur with the greatest frequency in the overall network. And we solve the following problem. Find a connected subgraph containing exactly one occurrence of each constrained color and at least one occurrence of each unconstrained color. So that relaxation will be a subroutine in the overall solution. Note that if we cannot find such a connected subgraph, then we will immediately know that the problem is infeasible, because this is a relaxation of the overall problem. The reason that the relaxed problem is interesting is that when we write it as an integer program, it'll have a smaller number of variables. Because without loss of generality, we can make the following assumption. If we look at the subgraph induced by the unconstrained colors. So once again, the constrained colors have to, the graph we're looking for has to be connected. The constrained colors have to occur once each, but there's no limit of the number of occurrences of the unconstrained colors. And so from that, you can easily derive the following property that in solving this problem, we may assume that if we look at the subgraph induced by the unconstrained colors, either all or none of the vertices of any connected component of that subgraph will lie in the solution. So the motivation for the relaxed problem is that we'll have a smaller number of variables in the integer program, because we don't have to have an indicator variable for each vertex. We only need indicator variables for the connected components of the subgraph induced by the unconstrained colors. Before seeing how we're going to use this relaxation in an overall algorithm, I'll also mention another very simple-minded technique that can be useful, especially in instances of the problem that are sparse. This is a forcing process, a little bit analogous perhaps to the unit clause process in solving satisfiability problems, where you can force certain variables in and out of the solution. So first of all, if you have a vertex which is the unique one of its color, it clearly has to be included in the solution. Once you've included a vertex in the solution, you can exclude any other vertex of the same color. You can also force a vertex into the solution if its deletion leads to an impossible situation, namely one in which you have two connected components, two separate connected components remaining, both of which have to be represented in the solution. And then there's a fourth, slightly more complicated technique, which allows a vertex to be deleted without loss of generality. So another tool that we have is this forcing process for forcing vertices in or out of the solution without loss of generality. So the overall algorithm that we have implemented, my postdoc Shuai Li and myself, he did the implementation, by the way, is first of all to apply forcing to include and exclude vertices. This may lead to a proof of infeasibility. Then, in the problem that remains, select a set of colors to be the constrained colors. These will typically be the colors of highest frequency. Solve the relaxed problem, obtaining a connected subgraph with one occurrence of each constrained color and at least one occurrence of each unconstrained color. If no solution to the relaxed problem exists, then the problem is infeasible and we can stop. Otherwise, we attempt to solve the problem on this subgraph H. If we solve it, that is to say, we also extend the solution to one that has one occurrence only of each unconstrained color, then we're done. And if no solution exists, then we may be able, using forcing, to find a certain color that is required to have two occurrences in the solution, in the completion of the solution to the relaxed problem. And we then add that color to the set of constraint colors and continue. So maybe it would be easier to explain how this algorithm works with an example. One way to generate examples is, in this example, for ease of representation, the graph is just a grid graph, a rectangular grid. The colors are the letters of the alphabet. And each vertex, each cell of the grid is a vertex, and each vertex is adjacent to its north, south, east, or west neighbors. And if you want to generate random examples or pseudo-random examples, then you just take a piece of English language text and you write it out row by row to fill in the array. So here are the opening lines of T.S. Eliot's love song of J. Alfred Prufrock. Let us go then, you and I, when the evening is spread out against the sky. So this gives us an instance of the problem. Again, the colors, the vertices are the cells of the array. The colors are the letters of the alphabet. We're looking for a connected subgraph with respect to north, south, east, west connections, which contains exactly one occurrence of each color. And we start by constraining the frequent letters, which in this case are E, T, H, N, and S. And those have been shown in red, and in white you can see the several connected components of the subgraph induced by the remaining letters, the remaining colors. And in solving the relaxed problem, we can assume that either all or none of each of those components is included. So we get, if we solve it by integer programming, we get a program with a much smaller number of variables than the original. So we proceed to solve the relaxed problem. And now the question is whether so in the solution to the relaxed problem, we have obtained a connected subgraph. Each of the red letters now occurs exactly once, but some of the remaining letters may occur more than once. We can try to apply forcing to see if we can infer without loss of generality the inclusion or exclusion of additional vertices, and if we're lucky, then we'll get a solution. Another possible outcome is that we'll demonstrate that this solution cannot be extended because some color has to be repeated. In this particular case, we see that one of the occurrences of A is necessary because the deletion of that occurrence would split the graph into two components, both of which would have to be represented. That forces us to exclude the other occurrence of A, and similar reasoning then tells us that the two occurrences of the letter R are both essential. So in this particular case, the forcing process has led to a particular color, in this case R, which we haven't been able to handle. We've been forced to include two copies of that color, and so we'll go back to the beginning and add the color R to the set of constrained colors. So now we have one additional constrained color. We solve the relaxed problem again. Now each of those constrained colors occurs exactly once. But we find now, after some forcing, that both occurrences of the letter A are necessary. So we go through the loop again, adding A to the set of constrained colors. And now when we solve the relaxed problem, we find that we can easily pick out, again by forcing, a feasible solution to the entire problem. So we've implemented this algorithm. The basic idea is that the relaxation is easier to solve than the original problem, and it points us to the troublesome colors which have to be added to the constrained set. And we get an algorithm that performs much better than the original individual algorithms based on dynamic programming and integer programming. Yes?
Does the set of constraint letters always only increase? Would you ever unconstrain something? Is that ever useful?
It might be, but in this version it always increases. So in an unfortunate example, you might add all of the colors might eventually become constrained. So, but our experience is that usually we're led to a few strategic colors after which we can either decide infeasibility or solve the problem. Yeah?
So the relaxed problem may have several solutions?
Yes, so we pick one.
So we just try one?
We just try one, and if we try the wrong one, then hopefully the forcing will tell us, no, that wasn't right because you can't complete that, and that'll point us to a new color that should be constrained.
It's not that you tried another relaxed.
No, that would be yet another variant, but that's not what we currently do. That could be tried. So there are various extensions that can be accommodated. For example, a vertex may be eligible to be considered as having any of several different colors. Instead of asking for exactly one occurrence of each color, we might relax that and allow for a few redundant colors. And we might permit the omission of a color, but have a term in the objective function that penalizes the solution that omits a color. And all of those can be incorporated into the various algorithms that I've described. Here's a reference. This is joint work with a group of people at the Tel Aviv University. And so that's my first example. Not demonstrating any profound general principles, but just illustrating how we start with some simple-minded solutions to a problem, and by, in this case, a particular relaxation technique, improve the algorithm. Some of you may have heard me talk about this next subject. I've talked about it in a few places, so apologies to those of you who've heard it before. I'm going to define a particular class of optimization problems called implicit hittingset problems. I don't know how to get rid of this stuff at the bottom here. Let's see if it, yeah?
I'm not sure.
Yeah, let's see.
Do you have for the future slides, is there a lot of stuff? Is it just going to be that slide?
No, it's all of them. Okay, we'll get by. We'll manage.
Okay.
So an optimization problem is said to be, here I'm thinking of some kind of constraint satisfaction problem. We'll say that an optimization problem is implicit if the set of constraints of the problem is defined implicitly by some algorithm that describes the set of constraints and can be used to generate new constraints upon demand. This is in contrast with the case where all of the constraints are written down explicitly to begin with. So we know many algorithmic techniques that hinge on representing constraints implicitly. So for example, for solving a problem, for example, of minimizing a linear function over a convex set. The convex set could be described by an infinite set of constraints, namely the set of all of its supporting hyperplanes, but we can't write that down. And so in famous algorithms such as those due to Gritschel, Lovász, and Shriver, we use the fact that we have a separation oracle which, given any point outside the convex set, will produce a constraint, an inequality violated by that point but satisfied by the points of the convex set. In integer programming, similarly, we use cutting plane methods. So we represent the integer program implicitly by its linear programming relaxation, in which all the facets of the convex hull of the integer solutions to the linear program are implicit constraints, and we slash away at that linear programming polyhedron to uncover an appropriate set of these implicit constraints to solve the problem. So that's the basis of the cutting plane approach to integer programming. In linear programming, we have a dual approach where it's the variables that are implicitly defined rather than the constraints, or if you will, it's the dual constraints that are implicitly described. For example, you might have a linear program in which the variables or the activities correspond to all of the different solutions of some knapsack problem. And so when you're running the simplex algorithm, you have an implicit description of a set of variables and an auxiliary optimization problem to decide which one to bring into the basis. So we have many examples of problems where we can cope with large implicit sets of constraints, and I'm going to add one more generic problem to that list. So first we'll start with the explicit description of the type of problem we're talking about. We'll call it the hittingset problem. You have a finite ground set with a weight, positive weight for each of its elements, and you have a collection of subsets which I will call circuits by analogy with the case of matroids, where you're required to hit every one of those sets, every one of those circuits. So the problem is to find a subset of the ground set of minimum total weight that hits, i.e. has a non-empty intersection with every one of these listed circuits. This is just the same as the standard set cover problem, except that we've interchanged the roles of sets and elements. So this is a standard, well-studied problem. And we've observed that a great many NP-hard problems can be expressed as implicit hitting set problems, where the circuits, the sets that have to be hit by the selected hitting set, have an implicit description. For the explicit hitting set problem, well, we know that it's hard. We know that its approximation ratio has to grow as the, thanks to results of FIGA, for example, has to grow logarithmically with the number of circuits. But we have a greedy algorithm which more or less matches that lower bound, but is very simple-minded. You just repeatedly choose the element that minimizes the ratio of its cost to the number of sets that it hits, put that element in the solution, delete the sets that it hits, and continue. There are some refinements of this, but even this straightforward greedy algorithm works reasonably well in practice. And we also have the magical C-plex integer programming algorithm, which is unpredictable in its behavior, perhaps less unpredictable thanks to Kevin's work, but is often observed to give optimal solutions rapidly. So in an implicit hitting set problem, the collection of circuits, the collection of sets that your chosen solution set has to hit, will have some compact implicit description, and there will be available a polynomial time separation oracle, which, given a subset of the ground set, either determines that that subset is a hitting set, that it hits all of the constraints, all of the implicit constraints, or alternatively, the separation oracle will produce a circuit that the current candidate set doesn't hit. So a simple example would be the feedback vertex set in a graph. You want to find a minimal set of vertices whose deletion yields an acyclic graph, and the separation oracle. So the set of circuits would be the collection of vertex sets of cycles in the graph, and the separation oracle, given a set H, will search for a cycle in the graph induced by all of the vertices outside H, and will return the vertex set of a shortest cycle in that subgraph, or else report that H actually does hit all of the cycles in the original graph. So there are many examples of problems that can be presented as implicit hitting set problems. So for feedback vertex set in a graph or digraph, the vertex sets of cycles would be the circuits, the sets that have to be hit. You have to delete at least one element from each cycle. For feedback edge set in a directed graph, the edge sets of cycles would be the circuits. For max cut, we observe that the set of edges crossing a cut has to induce a bipartite graph, so the circuits are the edge sets of the odd cycles. You have to delete from the cut at least one edge in every odd cycle. There's a typo here, my apologies. For the Steiner tree problem, the circuits are the edge sets of cuts, not cycles, that partition the required vertices. For maximum two-set, where you want to maximize, you have a two-set problem and you want to maximize the number of clauses that can simultaneously be satisfied, you have to delete at least one clause from every minimal contradictory set of two-element clauses. And there's a nice graph theoretic characterization of what those sets are. There are certain kinds of cycles in an associated graph. So we can easily have an oracle for that problem, and so on. The intersection of K matroids, maximal feasible subset of a set of linear inequalities. There are a host of problems that can be represented as implicit hitting set problems. So what I'm going to do in the remainder of the talk is to present a generic algorithm for attacking such problems, and then relate our experience with that algorithm for a particular problem that arises in genomics. There is no claim here that this generic algorithm would work well on every instance on every one of these problems, but we'll see what the characteristics have to be in order for the algorithm to work well. So let me begin with a naive algorithm for solving the implicit hitting set problem. So we'll start with the empty set of circuits and an empty hitting set. And in a general step, we'll have a set of circuits which will be a subset of the entire implicitly defined set of circuits. And we'll call upon an algorithm such as Cplex to find a minimum weight hitting set for that current list of circuits. Using the separation oracle, we'll either find that that set is actually satisfying all of the circuits, or more likely it doesn't, and we'll get a minimum cardinality circuit not hit by the set H, add that to the list of circuits, and continue. So this is an extremely naive algorithm where we keep adding to our list of circuits, each time solving an explicit hitting set problem to optimality, which is going to be an expensive proposition, and continuing until we've enumerated enough circuits that by hitting all of those circuits, the optimal solution that hits all of those circuits will hit all of the others. So this approach, of course, is flawed by the fact that we're solving too many instances of the NP-hard explicit hitting set problem. But apart from that, we see the general idea, which is that this general approach may work well in cases where there's a set of important circuits such that if we can manage to enumerate them, they will hold the key to the overall problem. So for example, in something like a vertex feedback set problem, if the intuition would be that if we list a strategic set of small circuits, small cycles, by hitting all those cycles, we'll be likely to hit the long ones as well. So the idea would be to execute something like this naive algorithm, but to modify it by guarding against the necessity of repeatedly having to solve explicit hitting set problems to optimality. So, so we need easier and cheaper ways of generating circuits. So we'll introduce a circuit finding subroutine. At a general step, we'll have a set of circuits and a hitting set for that set of circuits. Initially, both sets may be the empty set. And then we'll repeat until our hitting set gives a feasible solution to the implicit problem, until it hits every circuit in C star. We'll use the oracle to find a circuit not hit by the current set. And then we'll choose one particular element of that circuit arbitrarily. We'll add that element to our hitting set and add the circuit to our list. And in that way, we can keep generating distinct circuits until we reach a situation where the set H is in fact a feasible solution to the implicit hitting set problem. But of course, it need not be an optimal solution. But this is a cheap way of finding lots of circuits upon demand. So here's an overall algorithm. The basic idea is that we'll have layers of circuit generation. We'll find circuits using each of these layers until we get a set which is feasible for the overall implicit hitting set problem. And then we'll turn to a more sophisticated layer. And only if all else fails will we actually call upon Cplex to solve to optimality an explicit hitting set problem. So the first step is this naive process of executing the circuit finding subroutine. You have a collection of circuits. You have a hitting set that hits those circuits. You just look for another circuit that's not hit. You pick an element to hit that circuit, add it to the hitting set, and keep going. This is very naive, but very fast. Once you finally reach a hitting set this way, which is feasible for the implicit hitting set problem, it might be quite bad, it might be quite large. So what we will do is run the greedy hitting set algorithm to get a reasonably good approximation to the best hitting set for the current list of circuits. And if the oracle then tells us that there's a circuit that this set doesn't hit, we will add that circuit to the solution and repeat the greedy algorithm. If we finally reach a situation where the greedy algorithm yields a feasible solution to the implicit hitting set problem, then we finally, as a last resort, turn to Cplex, actually take the current explicit list of circuits, solve that explicit problem. If it's feasible, then of necessity it's optimal for the implicit problem. Otherwise, we go back to the circuit generation. So the idea is that we try to avoid as much as possible solving our explicit hitting set problems to optimality. But when we have no other method available for generating a new circuit, we finally pull out the big guns and solve using Cplex. So the metrics for the performance of such an algorithm would be the number of circuits generated, the number of calls to the Cplex solver, and the running time of the generator. So what I want to do now is develop one particular problem in genomics called the multiple genome alignment problem, and describe our experience with an implementation of the generic algorithm I just described. So the input will be a collection of genomes. At one level, a genome is a sequence of nucleotides, A, C, T, and G. But we will assume a kind of pre-processing that identifies certain pairs of sequences from two genomes that we will call an anchor pair. The individual sequences are called anchors. So an anchor pair is a pair of sequences occurring in two different genomes which are so highly similar that it could not have, their similarity could not have occurred by chance. Their similarity must be due to their having been derived in the course of evolution from a common ancestral sequence. So we will assume that pre-processing that will not be our concern has generated these anchor pairs. And we will now be able to think of each genome at a higher level as a sequence of anchors. And so the data that we'll be now working with is a list of anchors for each genome in its left to right ordering along the genome, and an indication of which pairs of anchors are so highly similar as to be called anchor pairs. And the problem is to align the genomes against each other in such a way as to demonstrate the similarity, as much as possible, have the two elements of an anchor pair aligned against each other. So I've given a more or less formal definition of what I mean by an alignment, but the simple idea is that you're going to take your genome thought of as a sequence of anchors and then put spaces in between those anchors to kind of stretch each of the genomes out. And you want to do that respecting the left to right ordering of the anchors in each genome, and try to get as many as possible of the anchor pairs to align in the same position. So we'll say in that case that an anchor pair is synchronized, and we want to maximize the sum of the weights of the synchronized anchor pairs. So the data in the case of three genomes in a tiny example would look something like this. Here we have genome 1. If we look at the first of the three diagrams, genome 1 has 6 dots representing its 6 anchors in their left to right ordering. Genome 2 is similarly represented. The lines between them represent anchor pairs. We can see we want to stretch out the positions of these dots, space them out, maintaining their ordering in such a way as to have each of as many as possible of these edges vertical, that is to say the two elements of the anchor pair occurring in the same position. But we also have a third genome, so we also have to look at anchor pairs between genomes 1 and 3 and between genomes 2 and 3. So what we want to do is maximize, let's say, the sum of the weights of the synchronized or properly aligned anchor pairs. The two-genome problem is equivalent to maximum weight increasing subsequence, and so is solvable in time n log n, where n is the number of anchor pairs. But for the case of k genomes, we don't know a method which is better in the worst case than order n to the k achieved by dynamic programming. So what we need is a better method for the case of the k genome problem, which, by the way, is NP hard. So how can we think of the alignment problem of these genomes as a hitting set problem? The ground set will be the set of anchor pairs. And our goal then is to delete a minimum weight set of anchor pairs such that the remaining anchor pairs can be simultaneously synchronized, so that all the remaining anchor pairs can be properly aligned. So we have to figure out what the obstacles are to aligning all of the anchor pairs, and those obstacles will turn out to be the circuits of a particular implicit hitting set problem. To find out what these obstacles are, we define the following structure: a so-called mixed graph which has both directed and undirected edges. A directed edge connects two anchors in the same genome and is directed from the left leftmost one of those two to the rightmost one. So the directed edges are enforcing the left to right ordering within the individual genomes. An undirected edge runs between two genomes and connects two anchors that form an anchor pair. And we'll define a mixed cycle as a cycle in this mixed graph which contains both directed and undirected edges for precedence within a genome, undirected edges for the anchor pairs, but the cycle must contain at least one directed edge. And as John Ketchachoglu observed for a related problem, an edge must be deleted from the set of undirected edges of each mixed cycle. To see the reason for that, let's look at an example. Suppose we have a mixed cycle. Would it be possible to align all of the undirected edges? If we could do so, then we'd have the following contradiction. For each directed edge, the position of its tail has to be to the left of the position of its head. For each undirected edge, if we aligned its two anchors, then the positions of those two nodes would have to be the same. And so as we go around the cycle, we see that we have a contradiction. And it turns out that that's the canonical contradiction. And so in order to delete some of the anchor pairs, we have to get a hitting set for the edge sets of all of these mixed cycles. Okay, so we've succeeded in representing the problem as an implicit hitting set problem. So we can run the generic algorithm that I gave, and we have various ways of constructing of defining the separation oracle. There are two ways to find, given a tentative solution, given a hitting set, a proposed hitting set, we would delete its anchor pairs, and then we would look to see if mixed cycles remain in the remaining subgraph. And we have a couple of methods. One is a variant of depth first search, and the other is to attempt to actually build an alignment in left to right order until you hit a certain obstacle which yields a violated mixed cycle. So we have these two methods of generating circuits, and so we can go ahead and implement the generic algorithm for this case. And it works well. Here we ran on 4,085 problems that were given to us by a group that's interested in comparing the genomes of 5 species of worm. And so we had many, many problem instances corresponding to different parts of their genomes. And we find that most of the problems are solved quite rapidly, within a second or so. The maximum time we allowed for any problem was an hour, 60 minutes. So we see that of the upwards of 4,000 problem instances, most of them were solved extremely rapidly. But there were 75 that took between 10 minutes and an hour, and there were 36 others that didn't solve within an hour. And on the right, we give the minimum, median, and maximum number of anchor pairs in these problems. So we see that the ones that took longer tend to have larger numbers of anchor pairs, but there's no rigorous monotonicity. So you see, as Kevin pointed out, sometimes problems of the same size have very different running times. But anyway, the algorithm did perform quite well compared with other algorithms for the same problem. We got interested in tuning the algorithm, and here we sort of connect with the kind of ideas that you were talking about, although our approaches were much less refined. Within the general algorithmic strategy, there are many possible choices for the particular separation oracle that we use, for the greedy algorithm, for which version of Cplex to use, parameter choices within it. And we did some kind of tuning by hand on a sample of the problem instances to sort of figure out which parameter choices for for the algorithm, including both the parameters of C-plex and the parameters of the overall generic algorithm, which parameters were best, and by tuning these choices not so systematically as a statistician would do, we found that we could improve the performance in running time by a factor of several hundred. So I think that this notion of tuning an algorithm on typical instances is a very important one, and if we get to the panel discussion, I'll try to talk a little bit more about that. So with this, I will stop and we'll be glad to take questions.
So about the separation.
Yeah.
So the different choices. So one criterion will obviously be how fast is the local itself.
Right.
What's important computation time. Are there rules of thumb for which circuits are the most strategic, as you said?
Yeah, well, yeah, about the only general criterion is cardinality. So we would typically look for the shortest cycles. There is another idea, which I mentioned that we had a kind of sweep algorithm that tries to sweep from left to right, and when it gets blocked, it finds the circuit that's blocking it. So that's another notion of strategic, where you actually see step by step what is the impediment to moving all the way through to a solution. But apart from those ideas, I have no general.
One derivation, you think it would be a theorem that justifies that approach to some conditions of the instance?
Well, we have a paper that we published, this was joint with, I always forget his name, Santosh Venkala, and one of his students, who may be here, who registered, let's see, his name is Karp, where we studied random graph. We studied the feedback vertex set problem on random graphs. And we generated circuits by kind of building a breadth-first search. And whenever you hit two edges joining at the same level in the breadth-first search, that completes a cycle. And we would kill the vertices in that cycle. And we proved that that comes within, stochastically comes within a factor of 2 of optimum in random graphs. Well, that was kind of a side project because I don't really like analysis of random graphs anymore. Yeah, GNP, yeah. GNP, yeah.
Maybe you have one yourself.
In my youth, I worked on this, but it's got to be out of the ways. No, it's a perfectly valid body of mathematics of some relevance, but it can be criticized. Yeah.
So I'm really interested to see a theorist grappling with the really practically motivated design of an algorithm without sort of having started directly from the proof some general property. I guess the thing you said to me at the very beginning of the talk about the sort of embarrassing effectiveness of the ones you described here resonated with me a lot.
Yeah.
And I wonder, and I guess what I sort of hope for from this community is sort of a closing of that gap between the embarrassing effectiveness and then the theory.
Yeah.
And what do you think the next steps in that process to try to close that gap might look like?
I'm afraid that I don't think there's going to be any universal answer. I think that we're going to have to consider these problems one by one. I very much like the body of work that you've done and the idea of applying statistical criteria for classifying instances and predicting performance. I think it's going to be hard to sell this particular group concentrating a lot of its effort in that direction because the kind of methodology is more in the realm of statistics and machine learning. But I think that some of that has to be done. I guess if I had a dream, it would be to try to emulate hack learning. Now, so in hack learning, you have this VC dimension, which tells for which problems you can get probably approximately two hypotheses. And I guess the analog of hack learning, which would be for which training sets of instances can you expect to get a really effective algorithm. But we don't have a VC dimension there. So I'm really a little bit stymied in where we should go. I know, Bernard, you've worked on some related stuff.
Yeah, I was thinking along the same lines as the dimension along the same program. But I want your question maybe somewhat philosophical, which is, in the realm of nature and biology, is there a profound reason how you treat evolution, which perhaps will bring about the fact that instances are easy?
Yeah.
And I wonder whether that would formalize this for the scientific thing, not just for the philosophical.
Yeah. Yeah, in the case of digital circuit design, I guess people believe that if somebody can think up the constraints of a satisfiability problem, if humans can conceive of what the constraints should be, then maybe it's easier than some crazy random set of constraints.
So this is going to sound kind of crazy. So here's something I've always wondered about, and I think I want to throw the question out because you were talking about biology. I've always wondered about, there's levels in biology, like the modules and, cell level. I mean, that one's very real, species level, and so forth. And I've always wondered whether the levels are real or whether they're a human construct.
Yeah.
And I think they're real, and I think they're necessary for evolution to create complexity.
Mm-hmm.
Do you have a reaction?
Well, I'll give a Rick Perry-like answer. I can't answer that question, but it suggests another question, which is often in biology when we're dealing with these abstractions, we're led to some kind of optimization problem where we introduce a scoring function. It might be a likelihood function, or it might just be some ad hoc weighting function. And we hope that if we solve to optimality, then we'll get the ground truth of nature out of it. And so a big issue is, can we expect that? Can we expect to be able to formulate objective functions to capture the ground truth? And I thought there was a very nice piece of work that Avram and colleagues talked about yesterday, where they talked about problems where the good solutions sort of cluster close to the optimal solution, so that you do have a good objective function. And the objective function really captures the truth. So I think that's an interesting direction. But to get back to your question about the different layers of abstraction, I too believe that they're real. Yeah. They're real, but they're incomplete. So for example, if you're modeling a cell as a bunch of little graphs of interacting proteins, you're forgetting about the fact that the cell has a shape and there are physical forces upon it. So you're leaving out a lot of stuff. But I still think there's a lot of validity to this abstraction.
More questions?
So another place I've heard this phrase, the unreasonable effectiveness of data. This is along with the AI community, where Peter Norton and Google, for example, says that very easy machine learning algorithms work better than complex ones when we have a lot of data.
Yeah.
And I find your results interesting because they're not about having more data, but about having average instances.
Right.
So
So you
what
find-
is the connection between
You find my results interesting because they're not about the right thing.
no, no, maybe a deeper reason.
Yeah, no,
Having more data is the more
I
obvious.
don't know. I mean, I agree that the world of computing is shifting from an algorithmic-centric thinking to data-centric thinking. And that's another thing that theory has to accommodate. So having not answered any of your questions with a little philosophy, I'll get off.